To start off with our Total Dilution and M1V1 versus equals M2V2 video, I want to explain a couple of vocab that people just might not know that is kind of essential to know for what we will be doing. So our total dilution is our first one. It's the product of the dilution factors for each step in the dilution process. That just means your dilution factor, which is, for this video, either be 1/2, 1/3, or 1/10. It's not going to be anything different from this video, but you can have, for example, like a 1/20 or 1/100 even. And then in our final dilution, we have the total dilution of a sample from its original state to a countable state. So that's a lot of jargon for basically exponents. So like for a tenfold dilution, our original flask, it's going to be a 1 times 10 to the first to, let's just say, the fourth one, which is flask, which is, sorry for these bad drawings, it's going to be 1 times 10 to the fourth. And then for our last one, which is M1V1 equals M2V2, M just stands for mass, V just stands for volume, and you're inserting them, and you're usually trying to find one of these variables. So I usually just insert X for one of them, but we'll get to that towards the end of the video, and I'll explain it again. So this is our 1/2 dilution, or our twofold dilution factor. So our TD and then our FD. Alright, so what we want to do with each of these is take a half of this, half of that, half of this, and then half of each. So half, you want, for this you want to take half of this, and so forth and so forth. So our total dilution, what is our dilution factor? It's 1/2. It's just 1/2 for all of these. It's whatever your dilution factor is. If we did 100 of these, our total dilution would be 1/2. So our final dilution is different though. So for this beaker, we want to take half of the concentration and put it into this one. So what would that be? 1/2. For this, or 2 to the -1. This, we want to take half of this. So what is our original? So we want to take half of our original concentration, which is 2 to the -2, which is 1/4. For this one, we want to take half and a half and a half. So was 2, or other words, 2 to the -3 was at 1/8 as a decimal, something different. Then for the fourth and final one, we want to take this. We want to take half of every beaker so far, so it's 2 to the -4th, and what does that give us? 1/16. So that's how we find our total dilution for a twofold dilution factor. This is our 1/3 dilution, or a threefold dilution. For our total dilution, we just want to take a third of this, a third of this, a third of this, and then a third of this. So for our first dilution, we want to take a third of the initial concentration. And then for our next one, we want to take a third of the first test tube, so that's another third, and so forth, so forth. So for this, you want to take a third of each one, which is shown up here. So whatever you have up here is your total dilution. For final dilution, what we want to do is compare all of these to your starting flask. So from our initial flask to our first one, we have a 1/3 dilution, because we're taking a third of the dilution, putting it in here. For our second one, we want to take this, we want to consider our initial concentration and put it here. So it's third to the -2nd, which is 1/9. For this, you want to take our initial concentration of this and compare it to our third flask. That'd be 3 to the -3rd, which is 1/27. And then for our final fourth, we will compare that to our initial beaker, which would make it 3 to the -4th, or in other words, 1/81. Now on to the tenfold real dilution.
You will need a stock solution, a pipette, and a container for mixing, such as a beaker or a test tube. Using the pipette, carefully measure 1 unit of your stock solution. This could be 1 milliliter, 1 microliter, or any other unit of volume depending on your needs. Next, add 9 units of your solvent to the container. If you measured 1 milliliter of stock solution, you'll add 9 milliliters of water. After adding the solvent, mix the solution thoroughly to ensure even distribution of the solute in the solvent. Now you have a tenfold diluted solution.
We're using our real-life applicable example for a 1/10 dilution. So our example is, if we have our initial concentration 5 micrograms per milliliter, and we're trying to dilute 4 test tubes, what would be our concentration in our 4th test tube? So that's what we're going to find out. We're going to figure out our total dilution and our final dilution factors first. So our total dilution factor, it's 1/10 because we're taking 1/10 of all of these. If you've been paying attention to this video so far, you should probably know that. 1/10, 1/10, 1/10. So our final dilution. I'm going to write this in terms of scientific notation just to make our lives a little bit easier when inputting this into the calculator. So our first one is 1 times 10 to the first, which translates just to 10. Because we're taking 1/10, so it's just 1/10. Our second one, or it would be this, our negative exponent. And our second would be 1 times 10 to the second, which is 1/100. Our third, because we're taking 10 times 10, it's equal to 100. And we're doing that for our third one, and that is 1/1000. And our fourth one, which is 1/10,000. This is the easiest way of doing 1/4 dilutions. So we need to find our initial concentration is 5 micrograms per milliliter, and we need to find a concentration for our 4th beaker here. This is how we're going to set up our equation. We're going to use our information. So we know we have 5 Ug per 1 milliliter. This is what this means. We're going to times this by 1 times 1 times 10 to the 4th. Just to make our lives a little bit easier. And then that equals, if you plug it in your calculator, 0.0005, or in scientific notation, 5 times 10 to the negative 4. So that is how we know in our 4th test tube, if we have 9 milliliters of water and 5 micrograms per milliliter of our concentration on our original test tube, we will have 0.0005 going to be a you try to prove that you have mastered serial dilutions. So we have our initial concentration. We're doing a 3-fold dilution, and the initial concentration of our beaker is 20 micrograms per milliliter. And we need to find the concentration of our 4th beaker. I gave you the total dilution factors. I'm going to let you try this. Please pause the video here. Now that you have solved the answer, we are going to go through it. So we have our total dilution factor here. We all know 1/3, 1/3, 1/3, and then 1/3 again. So what was our final dilution factor? 1/3 here, 1/9 here, 1/27, and then 1/81. If you had any trouble getting to this part, please go back or rewind the video, watch the other steps again. Okay, so if we need to find 20 micrograms per 1 milliliter, we would need to multiply this by our concentration here. So 1/81. So if we times 20, or divide, my bad, by 81, you should get, I'm going to round to the hundreds place here, 0.25. That is our rounded value. If we put this in scientific notations, it's 2.45 times 10 to the negative first. That would be the concentration of this in this. So for our first example of M1V1 equals M2V2, so we have if a 30 milliliter of a 2.54 meter solution are dilated into a 72.9 milliliter solution, what is the final concentration? So how we want to tackle this problem? I probably have your formula just up here, just for easy's sake, so you can refer to it. So our first part is diluting which is which part. So our 30 milliliter, is that volume or mass? That is volume, so we're going to highlight that. M probably stands for mass, considering you have mass right here. So that's probably mass. And then for our last one, milliliters, is this again. So we have all of that studied out. So now we know how we want to insert this into a problem. These are closest to each other, so I'd insert them on one side. So I would do 30.0 milliliters. It can go in any word, it's multiplication, times 2.54 meters is equal to 72.9 milliliters times x, because we're trying to find our x here. So we just insert that into our equation. We don't have to do any unit conversions for this. So we want to do 30 times 2.54. That gives you 76.2. We can do our units later. And then we want to divide this by this. So we're just going to enter our 72.9. And then you want to divide these two, which gives us 1.045 is our approximate proclamation of M2. So I'm going to now give you a U-try to help you with this. So for our final example of the video, we have an M1V1 equals M2V2 example. So a 0.994 solution of KBr, whose initial volume is 78.6 milliliters, has more water added until its concentration is 0.5 meters. What is the new volume of the solution? So what we want, so I'm going to let you try this one. So pause the video now and then I'll explain how to do it. Now that you paused the video and solved it, we're going to go through it together. So we have a solution that's meters. So that is our first M of this equation. So we're going to insert that in as this. We're just going to parentheses around it. Solution of KBr whose initial volume is 78.6 ml. So that means that this probably coincides with this. Has more water added until its concentration is 0.5. So we have 0.500 M. I'm just going to expand this a little bit. What is the new volume of the equation? So this is our V2 or our X. But we'll just consider it V2 for this. What we want to do is we want to multiply these two together. So she gives this, and we want to divide this by our 0.500. And then our unit, because this is M, our units should cancel out. So our answer should be less than M and ML. So what we want to do is we want to divide this by 0.5. That gives us approximately, I'm rounding to the hundreds place here, 156.26 ml. That is our approximate we're having. So this is our answer. This is the volume of our new solution. Thank you for watching my video. And if you need any more help with this, please go back and rewatch or find other people's videos to help you. Thank you and have a nice day.